Hi everyone, I'm Yunpeng Huang from the University of Tokyo. I'm very glad to be here to share my researches with all the audience here. My topic is the all-fiber mode locking by employing the band-induced polarization-dependent loss in the low V-number fiber. And this work was under the supervision from Professor Shinji Yamashita and Professor Jiyun Set. And our research funding was from the GSPS granting aid for scientific research. And the relevant result of this research has also been published in the Optics Letters in 2020. So here are the contents of my talk today. And first of all, I'd like to introduce some basic concept of the mode-locked fiber laser. And then we will move to the background and motivation part, where I will kind of give some ideas about the PDL and the NPR mode locking, and also some reviews of the previous researches around this topic, and also the motivation which drove us to propose the low V number fiber and the normal V number fiber. And next, we will move to the experiment part, where I will introduce our measurement system of PDL and band loss of different kinds of fiber, as well as our passive mode locked fiber lasers using the low V number fiber coil inside. So here is the mode locked fiber laser. Uh, this is the typical conceptual layout of the mode locked fiber laser. And as we all know, the mode locking is the most effective way for us to generate the ultra short pulse trains, and it can be used as a promising light source in the deep tissue imaging applications, because it can be used for the faster procedure, less invasive, deeper imaging depth endoscope, and also the deeper penetration depth clearer imaging microscope. And in the mode-locked fiber laser, there's one very important part, which is called saturable absorber. So it can help us to keep shaping the pulses over and over again by attenuating its Wien's intensity. So there are two main types of assay. The first one is called nanomaterial-based real saturable absorber, including, let's say, carbon nanotube, graphene, and so on. And the second type is called nonlinear array-based artificial saturable absorber, which can be used to take full use of the current effects inside the optical fibers. And the actually the new structure we propose belongs to this type. And here is the NPR mode locking configuration. This typical configuration contains the polarizing elements, a fiber polarization controller, or let's say a wave place, and which can be adjusted such that the maximum transmission at the polarizer occurs for the highest possible optical intensity. And the configuration then serves as an artificial saturable absorber, so it can keep shorten the pulse over and over again. So here is a very important part. It's called polarizer element, because it can select the transmittance of different polarization directions. So this ability, we call that PDL. So to know PDL better, here is the definition. It is a measure of the peak-to-peak difference of in transmission of an optical component or system with respect to all possible state of polarizations, so that we can use a polarization controller here to scan all the polarizations and input the DUT, and we can get the result output. And by these equations, we can calculate the value of the PDL very easily. So actually, there were some researchers have been using some components with the certain PDL value to initiate their NPR mod locking. For example, this research is from the Taiwan National University, and they call this the weak PDL configuration. So when their laser running in the weak PDL condition, this EDFL setup was directly pumped without a polarizer, so without this part, but only with this fiber polarization controller in which the band fiber provided the weak PDL. But unfortunately, indeed, for the weak PDL case, the mod locking is incomplete, or let's say operated in the intermediate region where the phase coherence of almost has not been achieved. So this eventually resulted in the wave packet with a complex temporal structure due to a relatively large intensity and phase noises. And this second research was from the Nanyang Technological University, and they used a defective WDM component, which was able to offer a 3.8 dB PDL inside their cavity and help them succeed in initiating mod locking. But this kind of method is not practical or controllable for the extensive NPR mod locking. So what we started to think about the conventional inline polarizer and the polarization dependent isolator. So both of these polarizing elements are based on the integrating a very high performance micro polarizer inside a rugged stainless steel package. So neither of them is able to get rid of the free space propagation. But in order to achieve the all fiber cavity, what we were trying to propose is a structure that based on the fiber itself. So our answer is to find a leakage mechanism inside the cavity. So if we can find a fiber which is very sensitive to bend, and if we can control the leakage ratio along the x-axis and along the y-axis, and maybe the bend loss could be different. In that way, we can generate and control the PDL very well. So how can we find a fiber which is very sensitive to bend? So here is a parameter that can help us. It's called V number, because it determines the fraction of the optical power inside in a certain mode which is confined to the fiber core, and a low V number makes a fiber very sensitive to bend loss and to absorption loss in the cladding. So by this equation, we can clearly find out that we can very effectively decrease the V number by increase its operating wavelength region. So what we did is simply using a standard single mode fiber 28 at 2 micron wavelength. But actually, this kind of fiber was designed for 1550 nanometer, but we operate this in at a 2 micron wavelength, where we'll change its V number from about 2.2 to 1.75. And as a comparison, we define the another fiber, single mode 1950, as the normal V number fiber, because its V number will be 2.27 at 2 micron wavelength. So we theoretically, by our theoretically analysis, we believe that the LVF should be more sensitive to bend than the NVF. So we carefully coiled these two kinds of fiber along the cylinders with different diameters and use our own PDL measurement system to measure their performance. So here, we have two figures to show the results. From the first figure, since the 2 micron wavelength light is weakly guided in the LVF, so the PDL and the bend loss of the LVF coils leap over 2.3 dB per meter and 2.5 dB per meter respectively when R smaller than the 21 millimeter. And in contrast, the NVF coils showed negligible PDL or bend loss in the whole measurement region. So consequently, we believe that the LVF is more suitable for band-induced PDL generation. And from this figure, it's also worth to find out that both the band loss and the PDL maintain a very good linear phase relationship with the number of turns, indicating that the PDL and the band loss properties are approximately uniformly distributed inside each turns of the fiber coil. And the loss coefficient could be easily derived since it can be like considered as remaining constant throughout the entire coil section. So here we use the LVF coils with different diameter inside our mod-lock experiment setup. And we found out only when the radius equals to 20 millimeter, we can easily get a fundamental mod-locking by tuning these two polarization controllers. And when the radius become 21 millimeter, we can only get harmonic mod-locking by very carefully adjusting these two angles. And for the other radius, it's impossible for us to get any mod-locking. So here are the recorded figures in the fundamental mod-locking state, and we can see that the bandwidth of in the frequency domain is 2.81 nanometer, and the central wavelength is 1925 nanometer. And according to the autocorrelation trees, we can find out the pulse width is about 1.42 picosecond, and its SNR is not bad. It's over 60 dB, and output average power is 4.2 milliwatt. It's not high because our system is based on the leakage mechanism. So after mod locking, when we look back, we do need a standard to evaluate the stability or the ability for different LVF coils for mod locking. So ideally, a fiber coil with higher PDL and lower bend loss is more effective for the impure mod locking, of course. So in the sets of data with different radius, although the PDL coefficient of the LVF coil at radius equals to 18 millimeter and 19 millimeter are significant, but the excessive bend loss makes them very impractical for mod locking applications. But for larger radius, like let's say 21 millimeter or 22 millimeter, also a small, also the bend loss is quite small, but the PDL value is not sufficient for the NPR mod locking anymore. So here we define a figure of Merit to represent the suitability for of different fiber coils for laser mod locking. It's called FOM equals to P times T, where P is the measurement of the polarizing efficiency and the T is the transmission of coils. So by this way, we can find out, we can divide this figure into different regions, and when the FOM beyond 500, we can get fundamental mod locking, and this region we can only get harmonic mod locking, and under a certain value we can never initiate mod locking anymore. So this is my research. Thank you very much.